Chapter 15 is all about waves and wave motion. Alright, so waves and wave motion. So the first question we need to ask is, what is a wave? And the answer to this question is a wave is just a disturbance that propagates through a medium. Right? So a disturbance and another word for propagate is moves. A disturbance that moves through a medium. And that medium can be things like air, water, a slinky, or anything like that. Alright, so a wave is just anything that moves through a medium and creates some disturbance. Alright, so that is the definition of a wave. And we have two types of waves. And those two types are transverse and longitudinal. So longitudinal. All right. And what's the difference? Right? What's the difference between these two types of waves? So a transverse wave is the kind of wave that you might think of the waves that we might typically think of. It's a wave that moves up and down like this. All right? And so the definition of a transverse wave is that the disturbance, in other words, this up and down motion of the wave at these points along here, the up and down disturbance, the motion of the disturbance up and down is perpendicular to the direction of motion. So the disturbance is up and down, but the direction of motion of the wave is forward. Right? So that's a transverse wave. And you can create a transverse wave by stringing up a rope between 2 points and maybe chopping it with your hand, and that'll send a pulse down the wave, or that'll send a pulse down the rope rather, and that pulse will be a transverse pulse. You'll actually see the pulse moving through the wave, the pulse moving through the medium, moving through the rope. Right? So that's a transverse wave. And a longitudinal wave is the kind of wave that you can create when you have something like a slinky, right? And so imagine you have a slinky and this is its naturally unstretched or uncompressed state, right? And you attach the slinky at this end to the wall or something, right? Or have a friend hold it, and you scrunch up some of this end really tightly. And then the rest of the slinky is stretched out, right? And in fact, it'll be stretched out even more, right? Because the distance between you and the wall hasn't changed. So this slinky will be stretched out something like this now, since you've scrunched it up, right? And what's going to happen when you release this compressed area, right? What will happen when you release that compressed area? Well, that compression will then travel through the slinky, and the slinky will then look something like this. And then eventually it'll look something like this. I can draw better compression than that. Whoop. Let's redo that compression. Right? So the compression travels this way down the slinky as it's moving, right? And so this means that the disturbance for longitudinal waves are in the disturbances in the direction of motion. Right, so our disturbance is in the direction of motion. And there are a lot of different types of waves you can make, but we're wanting to focus specifically on what are called periodic waves. Right, so periodic waves. And for now, we will concentrate more or less on transverse waves, but especially when we talk about sound waves, we will talk about longitudinal waves. But for now, we can think of a wave as just something that's moving along like this, right? So a periodic wave is something that occurs when you have, say, these pulses right here. These the high points in the wave represent the pulses, or a point along the wave, and a periodic wave is when the pulses are separated by equal amounts of time. So one way to get a periodic wave would be to stretch a jumping rope or a string or something like that very tightly, and then just chop it with your hand at regular intervals, right? At maybe every second or so, and that will produce a very periodic pattern in the wave, right, or in the rope. And so that is the definition of a periodic wave, and we have some things, some terminology to go along with them, right? So we're going to define the frequency and the wavelength. Alright, so we're going to talk about the frequency and the wavelength. So the frequency of a wave is simply the number of cycles in the wave per unit time. Right? The number of cycles per unit time. And the wavelength is the distance between 2 points on 2 different waves that are the same, or 2 of the same points on different waves. Or I should say on different cycles. Alright, and so the wavelength is generally going to be measured. The easiest way to measure the wavelength. Alright, so if we have a periodic wave here, and look at the crests, what we call the crests, the top of the wave, we call these the crests, and the bottoms down here would be the troughs. Right? But the distance between any 2 crests are denoted by 1 wavelength. And we measure the wavelength in terms of this Greek symbol lambda. All right. So that Greek symbol lambda is the way we denote the length of a wave. And this is just measured in distance. So a wavelength has units of distance. Right? And so one way to think about the connection between frequency and wavelength, right? I like to think of a train. So think of a train. And think of a train that has several cars. You're stopped at a railroad, and the train has several cars. They're all tied together, and it's moving along the track in that direction. Okay? Now, most train cars are going to be right around 52 feet. Right? Most train cars are going to be right around 52 feet. So if you add in the little bit of space on either side, then from here, from that point to that point, is going to be roughly equally spaced on each train car, right? So we can think of from this point to this point as being roughly 55 feet. And that means the wavelength of the train is going to be 55 feet. Now, what about the frequency? Now, the frequency in this case is going to be the number of cars that pass you in a given amount of time, say per second or so, or per 10 seconds. And so, let's think about this. Let's say that I have train cars whose wavelength are 55 feet, and the frequency of the train cars, let's say that there may be, let's say, 10 train cars in 5 seconds time. Right? So another way to think of wavelength is 55 feet per car, and my frequency is 10 cars per second, or 10 cars per 5 seconds, right? So what happens if I multiply these two together? I'm going to get lambda times f, and I'm going to get 55 feet per car times 10 cars in 5 seconds, right? Well, what happens here? Well, my units of cars cancel out, and I'm left with 55 times 10 is what, 550 divided by 5, and this is going to be in feet per second, and this is just 110, but what are my units? I have a unit of distance over a unit of time. This represents a velocity. A unit of distance over a unit of time is a velocity. And so, the velocity of a wave is going to be equal to the wavelength times the frequency. All right? So let's do a quick example. Let's do example 15.1 in the book. And in this case, we have a longitudinal wave. And it's traveling through a slinky, and it has a period of 25 seconds, or 0.25 seconds, and a wavelength, we denote period with t, and a wavelength of 30 centimeters. and we want to know what is the frequency, and we want to know what the speed of the wave is. And let's start with part A, right? So part A, we want to know what the frequency is. Well, the period, if the period is 0.25 seconds, that means that the cycle repeats every 0.25 seconds. So the period is the time it takes for the cycle to repeat. So that's the time necessary for the cycle to repeat. What that means is that the frequency and the period are inverses of each other. Frequency is cycles per time, whereas period is time per cycle, right? So they're inverses. So that means that the frequency is going to equal 1 over the period, and the period is going to equal 1 over the frequency. So since we're given that the period is 0.25, let's use this equation. So the frequency is going to be 1 over 0.25, and that turns into 4. And the units are hertz. So the units of 1 over seconds is hertz, and that means that there are going to be 4 cycles per second in this wave. Right? 4 cycles per second in this wave. And now we want to calculate the velocity. And we can do so, now that we found the frequency, we can say that the velocity is equal to the frequency times the wavelength. Well, we know what the frequency is, we just calculated it. It's going to be 4 hertz times 0.3 meters, or 30 centimeters. And that's going to give us a grand answer of 1.2 meters per second. Remember that hertz is 1 over seconds, so I multiply meters by 1 over seconds and I get meters over seconds, which is a unit of velocity, and that is my final answer. Alright, so the next video we'll look at how to visualize waves, and then we will look at sound waves. If we don't get that into the next video, we'll get that into the final video, and that will finish up the chapter. We will see you then.